I opened the carbon article on Wikipedia this morning, and then immediately it was like, oh no, I should have read all 42 of these last night.
Sounds like a perfect time to do a podcast.
They don't know what I know. They don't know.
Hey, this is Engineering Podcast. I'm Adam.
I'm Brian.
Welcome back for another Hang in the Laboratory. Thank you for joining us. And special thanks, as always, to our backers on Patreon who, lighten the load, making this thing happen by throwing us as little as $1 an episode. We should just eliminate all the other tiers. I feel like let's just make it $1 an episode. Anyway, those people help us keep this thing going. They get the episodes a little bit earlier. If you want to jump in there, go to patreon.zengineeringpodcast.com. And if you're like, who cares about that? What's that? I don't need to learn about a new thing right now. Just like us, rate us, and review us, whatever, that kind of stuff, wherever you are listening. What are we talking about this week?
Well, first, I just want to say that was an exceptional introduction this morning. It's clear that you've been up for hours. Even though it's earlier than we usually record, you've been like rearing and ready to go.
I'm jet lagged, so I just can't. I'm 3 hours further east in my brain than you are. And I sleep with a really good eye shade, so it's not even a light-based problem. This is entirely internal. I'm struggling with getting back on. It's not like, oh, it's still dark, I'll go to sleep.
You know, this leads me into my weird science article.
Well, first you have to the big one though.
Tease the big one.
Yeah, what are we talking? What's this week's?
Oh, we're discussing the science and chemistry and physics and everything behind carbon cycling on our planet.
Climate change part 2.
Climate change part 2, but we're not focusing on the climate change. We're just focusing on how the chemistry of our planet works, specifically around the element carbon, which is a important component of all of these conversations, and really the enabler of us to be here to have these conversations, I suppose, along with all the other elements, but carbon's a big one in there.
What do you got? Okay, so what's your fact?
Well, you mentioned that you're jet lagged, and this isn't like news necessarily, but I was reading an article that was talking about our circadian rhythm. That's the right term, right? For your biological clock. It's kind of the fun term. Yeah. And it was saying that there is a measurable biological clock in every living creature on Earth, all the way down to like single-celled organisms. You can test and disrupt their expectation of like a 24-hour cycle based on sun and moon, right? Which is kind of obvious, I guess, when you think about it, right? It's a pretty important component of being alive on Earth, which is going to lead into our episode here, I think. But it was just really interesting thinking about the idea of plants like resting at night. I don't know how tested these theories were. The thing I was looking at, I didn't dive too deep, but it was showing imagery from their study where plants like noticeably relaxed in the evening, which is maybe anthropomorphizing it a little bit more than it needs to be, which put off my red flags a little bit.
But the central point holds, which is that there's no way, like, I've seen the same thing in the context of our urban plants. Do they fruit differently than plants that have a steady, like, sort of circadian cycle like that? You know what you're saying? And they behave differently. I don't. It's like, never mind the noticeably relaxed part, right? That granularity is not necessarily even helpful unless you're a farmer. Well, but tomatoes are smaller when they grow in the city.
Yeah, and you've got, right? Got all the behaviors, right? You've got flowers that open and close during the day, or when it's hot or cold, or in the morning. You've got plants that move to stay with the sunlight during the day. It's crazy behaviors, right? And And it was interesting to think. I'd never thought about it down to a cellular level. But that life was here for a long time, and the sun was important to them too, right? The sun has always been the primary god. So
the primary god
until recently.
Okay, that sort of relates to my first one, which is just a tiny little nugget. Chickens lay eggs once a day. I had no idea.
I've always been absolutely astonished at the rate at which chickens produce eggs. They're huge relative to their body size.
Yeah, I had no idea that chickens were such prolific producers of an edible substance.
How do they do that? Can you imagine if humans laid babies once a day?
You would care a lot less about your baby.
That's true.
What that would result in.
You could make smarter decisions about your kids.
The second one is actually news. As we're recording this, I think, or sometime today, NASA is launching the InSight lander bound for Mars.
Ooh.
So this is a lander and not a rover. So it doesn't drive around. It just lands in one spot and then does a whole bunch of testing.
Cool.
The only one I remembered that was cool enough is it has a drill that can actually go 5 meters.
Wow.
Into the ground.
That's very deep.
Yeah, it's very deep considering the deepest we've been otherwise is half an inch.
5 meters would take you like days. Maybe
a centimeter for our international listeners.
What is the discovery? What is it trying to discover?
It's all seismic and geological experiments. So there's also a thing that like detects seismic activity, like if the planet wobbles.
Right.
Then there's also one that's a lot more sensitive than we would think of as like seismic. There's one for detecting earthquakes, but then there's a sensor to detect magnetic wobble and things like that. So they're trying to figure out if the core of the planet is solid or liquid, and you can tell that by the way the planet wobbles. You can't see my hands, but I'm doing a great like
you're wobbling all over the place.
I'm wobbling all over the place.
Right, I think we think Mars's core is solid, right? And that's why its atmosphere is gone and why it gets a lot of radiation on the surface and why it's kind of uninhabitable. But we're not sure. And maybe a long time ago, it was like Earth and lush and green and had an active metal core shielding the planet, right?
And so I was stoked to use this as my science nugget at the front of the episode here, because it relates to exactly the conversation that we keep having as part of climate change. The extent to which science in the fields relating to climate change is advanced is that we're going to other planets to poke at things 15 meters in the ground and going, well, we know so well what's going on over here. We're kind of bored with it. Let's go see what's going on at this planet all the way out there. See what it tells us about our planet as well in terms of its formation, right? Like it's a planet at a different point in a life cycle that will eventually happen to all planets. They just die. It's like shit, the magnetic field shifts or goes away, and then everything on the planet just cooks because the sun.
Yeah.
That was dark.
I don't think it's dark. I think it's interesting. Right? And Mars could have had whole civilizations. It's not just science fiction, right? The planet, conceivably, it's in the habitable zone where Earth is. Every nerd has heard of the habitable zone. We've talked about it before. And Mars, if these features of the planet were different 1 billion years ago, they had plenty of time up there for animal life to emerge and to grow. Could be the stuff that lives on Earth, right? There could have been a time when both planets had the same DNA-based creatures living on them, right?
And there's also a possibility in that timeline that we can never even find that out, and it's still true.
Oh, we absolutely can't.
Because nature is metal. Nature eats that shit in the end.
Nature crushes everything immediately, like literally, right? It crushes things and devours it and reconsumes it, and civilizations disappear, right? We think of I always find the numbers around dinosaurs to be really interesting, right? Because they're wildly ancient creatures. People know we're talking hundreds of millions of years, and then you even have other fossils, right, that we have that are from even longer ago than that, like the earliest life that are sizable enough that we can see them. And there just aren't that many of them found. And the T-Rex number, I think, is sitting right now. There are 13 T-Rex skeletons in the world. They're worth tremendous amounts of money, right? Like there are T-Rex skeletons on the open market for like collectors. And they're not complete. They're individual pieces of bones, and they're like 10% complete, but we kind of know they're a T-Rex. We kind of think it's the same species. And we like to think of all this stuff as like, we know everything about dinosaurs. There were T-Rexes everywhere. But we just don't have that much information. Nature reconsumes all this stuff and turns it into other things.
Okay. So this particular episode, we are diving into some of the science behind the stuff we talked about before in terms of what is climate change, what the fuck is it, right? But also, in the meantime, we've recorded an episode with a really cool guest that'll be the next part in the climate change series. So stick around for that. But the depth of our conversation with that guy kind of calls for an intermediate episode where we're like, hey, here's all this other stuff to maybe think about before we talk to the dude who's just going to keep referring to carbon capture as a thing he assumes you understand, which is fair. We told him to assume that.
Also, I'm like bursting with information that I want to talk about.
The caliber of this deep dive it's up there with our early episodes on cameras and things. Like you're literally reading books on it. When I said, okay, you want to do this? You said, let me go get some books off my coffee table.
It's a fun topic. It was fun as we were just talking about the various little science highlights there at the beginning. You just can't get away from the things that describe what's going on.
Problem.
Well, not even from a problem sense, just from the concept of cycling of Earth is kind of, it's all of our science, it's all of our matter, all of our physical matter on the planet. It's all of existence as far as we're concerned as little terrestrial beings crawling around at the bottom of the sky ocean.
It's at the core of all science. Like to be able to poke at science news until I find a thing that'll segue into the headline bit is not hard work.
No, it's definitely not hard. The instant you said seismic, I pictured like I pictured like the opening scene of Tremors, where the geologist, the main female character in the movie, she's cruising around like firing shotgun blasts into the ground to measure like geologic vibrations in the earth. And then I just started picturing Mars, and I started picturing the setting in Tremors. And I think we've got a great script for the next Tremors movie. You get Elon Musk in it, right? He would love to be in it.
The problem with this, the whole time, I just felt the need to introduce Tremors for people.
No, they can look it up.
We watched this a whole lot of times.
I watched it all the time. I loved it. I don't know how many people know about Tremors, but I thought it was super fantastic.
It's a Kevin Bacon movie from the 90s, early 90s.
Kevin Bacon, and then the other actor looks like the guy from Train, but I don't think it's the same person.
And it's a monster movie with these fucking worms that try to kill him the whole time. Anyway,
it also has the dad from the show with Michael J. Fox, which I always thought was very strange. And Reba McEntire. It has in there. Everyone's good in it.
It's an interesting cast, yeah.
Fred Ward is the other guy.
You'll recognize
I love him in it.
Fred Ward.
Well, if you think about all the things that Elon Musk is doing, if there are those Tremors monsters on Mars, like we're in trouble. He's going to go up there and dig all these holes in the ground with his boring machines, and they're going to be like all over the place. We're sending these rovers up there to dig holes. Like we're just aggravating them now. And then we're going to...
And if you want to run way deeper than Tremors with the idea of worms in your planet, dude, I recommend Dune.
Oh, intense.
So when we were leading up to this, when we were talking about this, you said life exists solely to create carbon chains.
Yep.
Carbon's that important.
That's what we do all day, or that's what plants do all day.
What is carbon?
What is
carbon? Carbon. What is carbon?
What is carbon?
Yeah.
Carbon is just an element like hydrogen and helium and oxygen, and it is a very popular one in the universe. I believe it's the fourth most common element by mass, which means there's a lot of it. There's a in the universe, right? So there's there's that reason that it's popular here on Earth. And I mean, like, it's like pop culture popular too, right? People talk about carbon all the time, at least here on
Altered
on the
carbon,
West
carbon
Coast,
fiber, carbon
where
hardened
we
steel.
got a craze for carbon craze. It's a very unique element in that you're able to create a lot of. Excuse me, let me rephrase that. The universe is able to put it into a lot of different formations. I believe it's the element that's able to enter into the most structures of any known element. And so if you think about molecules, right? Like water's a molecule, right? It's a mix of a couple elements, H2O, hydrogen and oxygen, how they kind of go together. If you think about those, I was thinking about these in terms of, I was just talking to someone about these toys the other day. They're these little wooden toys I had as a kid, and they're like little round wooden blocks that you stick like wooden sticks in. You can link them all together. They're kind of like Lincoln Logs, but they're not Lincoln Logs. They're kind of like Legos, but they're not Legos. You know what I'm talking about? They're like little green circles and squares, and you put sticks in the side, and you can build all these structures out of them. Carbon's able to be thrown into thousands and thousands of different structures, which is weird compared to other elements. It's very versatile. It can do a lot of things. It can bond with a lot of other Tinker Toys. Tinker Toys. That's it.
This is the state of our world of information right now. I Googled sticks and circular hub children's toy, and the first answer was the right one. The second answer was an opportunity to buy some.
Tinker Toys. Perfect.
Sorry.
Carbon's
Tinker
like
Toys.
the ultimate Tinker Toy.
Let's take this back a second, even further. Earlier we were talking about geological time scales and Mars and all that kind of stuff, right? And so the thing that's interesting there ends up being an introduction for just the idea of chemistry before we even get to carbon, right? Like chemistry is a whole field of science that is looking at the stuff that happens once everything dissolves. Right? So on a long enough time scale, there's the possibility that on Mars, we don't see evidence of the worms that used to live there or whatever. We don't see fossils because chemistry has happened to them for so long that all we see is constituent
right, everything's
elements.
been moved around and broken up and like physically crushed and changed in heat and pressure. And then with that, you get all this chemical cycling, right? Everything changes. We don't like day to day. We live in an environment that's very stable, right? Our homes are like 60 to 80 degrees, depending on what you do outside. We can't live outside of like mostly
and predictable. Like we can do these things with chemistry that to a normal person look like some clear stuff in a beaker and some other clear stuff in a beaker. And you swirl it up and you know with great certainty what's going to happen. Sometimes it explodes.
Well,
That's
I think
not good.
the most interesting place that people encounter chemistry, I think, and you don't think about it this way very much, but cooking is all chemistry, right? If you think about what you do in like a chemistry lab, what your professor's doing, and then what you do in your kitchen, it's identical, right? You're putting fancy equipment that you bought that is different than everything else in your house that's specifically for that on a flame, and then you're putting materials in and mixing them together and adding heat and pressure and mixing them around and lids and pouring them
and within a certain margin of error, it's predictable insofar as, hey, I got bread again.
Totally.
It's edible.
Right. You set specific temperatures to make certain chemical reactions happen and to not kill things or to purposely kill things, right? Like you cook meats to certain temperatures to kill things in them. And so you're just like, you're doing chemistry there.
So you don't get worms.
all the things that we like about our food, all the flavor combinations and like the burned flavor of meat that people like, there's like a culinary term for that, but that's all chemistry, right?
Maillard reaction.
Oh yeah, that's the word, right? I have this book
I know that
I've actually never used, but I like to talk about. because of my enthusiasm to wanting to use it someday. I think it's called like Cooking for Geeks, and all of the recipes, each chapter I think is a recipe, but it's also like a chemistry experiment. So it talks through the chemistry of what's happening with your food while you're making that meal. And it gets into all that stuff, like what's going on. And at some level, I bring this up because it's the idea of converting matter is not encountered normally in the day, right? You don't want your like keyboard to turn into ooze and like become something else while you're using it. So we try to build these things that stay very stable in our environment. Your car doesn't like just turn into some other thing throughout the day because it got hot outside. But when you're cooking food, you very purposely are trying to change it into something else. Like think about pancake batter that's chilling in a bowl. It's like this weird goopy shit. And if you stick it in the fridge, it becomes something. If you put it in a pan and add heat, it becomes something. If you mix it up with water and oil, so there's all this chemistry happening. And it's kind of like the only place where you are like purposefully doing chemistry every day and where people just encounter it all the time.
And a lot of it involves carbon.
Right.
Right. So back to what is carbon. So carbon is an element, which is those are the constituent pieces of the things you're studying when you do experiments in chemistry. Because you're like, oh, this molecule detached from that one, or like this atom of this element left this molecule, and then this other thing hooked into it, and then this reaction happened.
Totally.
Right. Carbon is super versatile. A lot of stuff sticks to it.
A lot of stuff wants to hang out with carbon. It's popular.
And it arranges itself in a really interesting way. If you add it to the right elements to get steel, you can build fucking skyscrapers because we know how to manipulate carbon. Super involved in everything we do in life. Everything life seems to do has carbon tied to it. It seems to be the central facilitator of what you were saying. This all we seem to want to do is create more carbon chains.
It's a very important part of our body
and consume carbon
I think it's
chains.
the second most prolific or second most common element in your body. It's behind oxygen. So it makes up a considerable part of your weight. Like your weight of your body. If you picture coal as carbon, which isn't totally correct, but kind of correct, or like pencil lead, a big portion of your body is made of carbon. So picture like both of your arms just as like black, crusty coal. That's kind of accurate. That's like the carbon content in your body.
Statistically speaking, it's not far off, right? So then the idea is on this time scale, chemistry happens in cycles. It relates to the predictability of everything I was just talking about. And so when people talk about carbon as it relates to matters of climate change, in keeping with the theme of the episode, right? They talk about the carbon cycle, which is it eventually gets to our use of things like fossil fuels, but more important to understand there's this part of it that it just is going to happen. Like there's partially a cycle of these molecules around a closed system, which we talked about in the previous episode, and they behave thusly, right? That's the broadest possible view I feel like I can give you of the notion of the carbon cycle.
Yeah, I mean, the carbon cycle is discussed at varying levels of granularity relative to our ecosystem, right? You've got the carbon cycle of the planet, right? Of our whole system, of our whole existence, basically, right? Where is carbon on our planet and how is it being used? How is it being used to make your body? Where are you getting it from? How do you use it? What's it used for? Where does it go? What happens to it when you die? Same thing with plants and animals and our atmosphere and the ocean and the ground. Where did oil come from? Petroleum. Where did coal come from? What the hell is it? Right? Why is it there? Why do we dig miles and miles under the ocean and then miles and miles under the ground to get this goopy stuff?
To get to how we get that goopy stuff, I think you have to start at plants. because that goopy stuff is just concentrated plants.
It's
Millennia worth of squeezing plants and getting it wet and squeezing it and getting it wet and squeezing it.
That's a perfect description.
Worms help with that. We got worms in the mix again.
Well, that's
literally creating compost.
We have a compost bin that we've been using, which I think we've been making some good compost. A lot of the stuff I've tried to plant with it has not gotten anywhere.
Over the weekend, I learned don't put meat protein
yeah.
into the compost thing. It attracts flies and rodents.
Yeah, and you can't put that in home compost either because it doesn't get hot enough and the chemistry won't break it down.
So what are plants doing? How do plants play a role in the carbon cycle?
At every stage of this conversation, I want to say I'm bursting with excitement to talk about it. But specifically at this one, I find it to be kind of the most important and the most interesting because it's where it all gets started, right? And I don't want to limit us to plants. I think we should go a little broader here and say creatures on Earth that possess the ability to photosynthesize, who can capture energy from the sun, which long ago evolved in single-celled organisms. And
Alan, frequent guest on this show and now co-conspirator in my professional life, used to advocate for genetic research into making human skin cells, breeding photosynthesis into human genetics, so that we could just use the same materials that a plant uses to create energy to run our bodies. But what he mostly got a kick out of was that it would mean we'd have green skin.
Or even better, we'd have like protrusions with green leaves to get more surface area.
Yo, we would just look like ants.
We'd look like those weird animals that look like trees.
Anyway, so the point of photosynthesis, though, is you're saying, okay, let's go broader than plants. The broader step past that is literally everything in the system, ecosystem Earth, that uses the sun to create energy. The problem is at that level of, maybe I'm flying too broad with it once you say that, but that's just everything in the system. The whole thing is a study of what do you do if you have this hunk of rock and then you throw radiation at it in a way that radiation gets used and that energy stays in that system.
Well, this is probably a good separation, actually. We should, before we introduce the Earth with living creatures, wherever you want to draw that line, life, non-life, let's go back, like before there were single-celled organisms, before plants, before animals, right? Because the key to this whole conversation, and this is a piece that comes up by necessity in like every conversation we have, right? These fundamental rules of thermodynamics. You need energy for stuff to happen in the universe, right? You need energy to drive your car to like make it go forward. It uses energy and it like converts it into kinetic energy. So the car is like physically moving forward and a lot of other things happen. But ultimately the piece you got to get there is it takes energy. And in a way, you kind of lose that energy. It's not a great way to say it scientifically, but you can't drive your car and then like recapture the energy you used to drive your car and then drive it back the same distance. On some level, energy dissipates.
Right. So when you say lose, it's not that when you say you lose energy, it's not that you don't know where it went. Right. It's just not stored in the form in which it was stored.
And it's not before. Reusable, kind of. Energy isn't totally reusable.
We have a whole episode you should go check out if you want to talk about this piece, where we talk about the difference between internal combustion engines and electric motors. And they're all just questions of efficiency, right? And there is no 100% efficiency. So when you take power out of a battery and you put it in kinetic energy forward, you're losing a lot of the energy that was stored in that battery to things that just are part of using it in the world for the stuff we're never going to stop using it for.
That's an important notion because The same is true. The same thing that's true of our technologies, batteries and motors and engines, and the same thing that's true there is true in biology. It's true in life on Earth, right? So
every process in the world,
every single thing that's going on, every thought you're having, every movement you make, everything you pick up, everything you eat, everything that's happened in your entire life is using energy and bleeding it off, right? So for things to happen on our planet, for there to be anything, literally for there to be anything, for there to be like movement, for the earth to change shape, for like water to flow, for rocks to move and change and mountains to grow and people to live, energy needs to come in from somewhere to make that stuff happen. And in the process of that, the energy kind of gets used. And then for those processes to continue, you need more energy to come in. And so that's where we get back to the sun god, because that, for the most part, is the Earth's entire source of energy, right? Everything that's happening on our planet, the wind blowing, water flowing, icebergs being created, icebergs being melted, like all of this stuff is coming from the sun. You've got some energy coming from the core of the planet, but in terms of like life, like creatures, that's not as important. In terms of like long-term mountains and stuff, that's very important, but we don't need to focus on that too much right this second.
It's literally a global geologic scale that you're talking about. Once you take it back that far, we're way past cave paintings, because the caves don't exist.
Right, the
environment
the caves have
carve
been,
them.
or alternatively, the cave that you painted has been crushed and reproduced and turned into other caves over and over and over again throughout history, millions of times.
So what this comes down to is breaking carbon chains is a really good way of producing energy that then we feed into this life system, whatever it might be, right? Plants do that one way. Animals do it another way, because we have to eat plants and animals to create the energy to run our bodies, right? Plants have to eat some other stuff and spit out some other stuff in order to use take part in this process of carbon. They create carbon chains by consuming radiation, right?
Plants are kind of, I mean, they're both. They participate in some consumption there too, but plants essentially are growth, right? Their physical creature is carbon chains. They're creating these chemical structures made mostly of carbon and hydrogen, and they're building their body out of it. And in doing so, they're using sunlight to do it. They're taking energy from the sun to create these more complex molecules that require energy to put them together. Like it, as I've been thinking through like analogies here, I just keep going back to things like Tinker Toys and Legos and stuff. Like it takes, it's not a perfect analogy because there are these other ways things work. But if you think about hydrocarbons, if you think about carbon chains, the things that physically make up the like structure of the plant in certain ways and make up like important molecules within the structure of life, it takes energy to take those Lego parts and put them together, because they're putting together something that doesn't just sort of like naturally occur in the universe. If you think about the structure of your DNA, at that level, I'm not sure people think about like the structure of matter in the world, like rocks and stuff, but it's just much simpler. Before there were living creatures that were capturing energy and producing the complexities of the human body or of a plant matter, you just had less complicated structure in these molecules. And so to create things like DNA, to create things like fats, right, and proteins, these things people talk about with nutrition all the time, you have to take energy. You have to give energy to something, and then it has to take all these little Lego pieces and put them together into structure. And so in doing so, you have this concept of embodied energy, where you have used energy to create these complex molecules, and then all of a sudden you have something that's energy rich. And so plants are fantastic at this, right? Photosynthesis is the thing that was invented by life to capture radiation from the sun, use that energy to do chemistry inside of themselves to build these molecules. And now we eat them because those molecules have that embodied energy. They have starlight energy in them, and we use that to eat so we can grow our brains and talk about it.
All of that matter having consumed the radiation and then use it for stuff, and then is compressed over millions of years, like we talked about. It's all just long tail photosynthesis, right? It gets back to the problem of it's accidentally too broad when you hit that point, because you're right. But what we're trying to do is find different ways to manipulate it for the stuff that we need, which was the previous episode, right? And so this is where you get to the term carbon capture, the idea of, for what humans do to drive everything forward, what animals broadly do, any life that isn't plants does, is consumes the plants and turns them into stuff. And we found this like resource of goopy black condensed plants to do stuff with. But it turns out to create that energy, you have to release carbon into the atmosphere. So never mind the oil piece, because I feel like that gets dark. But like cows eat grass and they fart.
There's an interesting like relationship here when you really stop and think about it for a second, between fossil fuels and plants and what we eat and what we use to energize our planet, to drive cars and stuff. And like you mentioned, fossil fuels, oil and coal and natural gas, are dead creatures, right? It's dead. It's organic matter. It's plants and single-celled organisms that photosynthesize. They captured all this energy from the sun over their lifetime, right? For plants, it can be centuries, right? Trees can live for centuries, and they're capturing sunlight, and by capturing sunlight, they're then capturing carbon, and they're building this energy-rich material.
Yeah, like they're just sucking up elements from wherever they can get them via their root system
from
their
everywhere they can possibly
system.
get it. They're trying to be as efficient as possible, right? To consume these resources from the planet, just like we do as humans. And they build their homes, which to them, from their perspective, like is their being, right? They're not building a house outside of their being. That's some weird abstract human shit. But they and so they capture this energy, and then we eat them to live, right? We eat plants, or we eat cows that ate plants. And if you then realize that oil and coal and natural gas all come from plants, it's from plants from long ago, from long periods of time. We're just eating fossil fuels, essentially. It's the same stuff, right? When you start to think that, like, wait, our cars run on oil, which seems really abstract. You go to a gas tank or to a gas station, you've got this tube, and it like smells funny, and you know that it's going to explode if your like beeper goes off and all this crap. Delete that. And then
No.
And then and so it feels different, but it's exactly the same. We eat plants, and we're eating the same material. We're eating it for the same reason. We run on the same thing. We need that same embodied energy, and it's just coming from the sun. It's just the same cycling.
Well, it kicks back to a common theme, which is at one side of this conversation, the best source of energy that we can use to put energy into the system is, one, it's the one that the plants use, which is interesting and worth knowing. It's also coming from a giant thermonuclear reaction far away in the sky that is performing a chemical process that we can't replicate
very well
locally as a source of energy. The best we've found is you can suck some off of that energy. And I say we, including the plants, right? They are really good at eating shit. If you just leave stuff out in a field, it goes away pretty fast, unless it's made up of other certain elements, right? That system sucks stuff right back into it.
Right.
The remarkable
living creatures on Earth are phenomenal at consuming and recycling, right? That's the whole point, right? We talk about the Earth, I'm sure on tons of other episodes, we talk about the Earth as like a science experiment. It's this sort of closed system in terms of material. And the only thing coming in or out is starlight, is sunlight, is energy from the sun. And so all of the creatures on Earth are we're just here cycling stuff. We're just here. We live our little lives, which seem like they're an eternity, right? 100 years if you're lucky to live on Earth as a human. But you're just you're just a pile of stuff that like was a plant 100 years ago, was a tree for a while. It was a T-Rex. It was a bunch of like seaweed in the ocean for a long time. Then it was a fish and a shark. And then you were a rock for a while. And then you were a rock again, probably for millions and millions of years. And you were probably oil. And like, you're just part of this cycle. You're just this pile of stuff being cooked on the Earth's kitchen.
When you follow that scale in that way, you should realize from a broader philosophical, sort of like Zen view of it, you have already achieved what you frequently lust for. You're just floating around in a sack full of saline, having thoughts, doing stuff. And you lust to put your body in a sack full of saline so you can just
This
float.
is a difficult period in this little local part of the universe, right? Where I have to be me and think about all this stuff. It's really chill when you're just hanging out as a rock for 10 million years, right? You're just couch surfing, Netflix and chill. You're just a rock worming in the sunshine. That's great.
And so here's the thing about a system like that gets us to the climate change piece. Our concern as a consciousness floating around in saline sacks is that in terms of the possible life scale of life, timeline of something flying around in space, like we're in this really narrow band that we sort of have to make continue to exist, or else we just die and dissolve also. And then some other future race goes, I wonder if there were people here. Probably not. And then moves on to another planet.
Yeah.
And so we change our atmosphere around us to make that continue to be the case.
Well, you're completely right.
It takes a lot of energy.
As far as we know, all of the chemistry and all of this cycling and all of this stuff that's happening on Earth is happening everywhere in the universe, right? It's happening more simply because, like Mars, for instance, like we were talking about, our moon, there's not as much stuff there. There's not as much variety. There's not an atmosphere. There's not liquid water. They're not creatures. They're not plants. There's not this. There's just not the chemistry happening on the moon is less complicated. There's just less of it happening. On Earth, it's wildly complicated, right? You have just almost an unimaginable number of different types of chemical reactions happening and different structures being built. Just think of all the things you can build with the Legos on Earth. There are just fewer Legos chilling on the moon, and there are fewer opportunities to build neat things out of those Legos. So
we're moving that stuff around, both to be comfortable, to make life persist, all that kind of stuff. And over top of this whole thing is what I was saying earlier, what we got to before. It takes energy to make energy. There's no way we don't bleed energy in this system. That's one problem, right? We need energy to make this keep happening. We currently are using as a primary source of storage for this energy source, a thing that is rapidly making it so that our biosystem might just kill us all. Like our ecosystem. We might wander as a planet out of that band, and either we have to adapt and it's going to be aggressive and a lot of people are going to die, or we have to figure out this solution to maintaining that ecosystem.
Well, let's talk about what we're doing chemically with these carbon-based structures.
What
is happening chemically, right? Because we've talked about this initial piece, right? Plants, really dumbed down, really simply, they get energy from the sun, and then they pull carbon from the air, carbon dioxide. We know plants breathe, quote unquote, air quotes, carbon dioxide. They breathe that carbon dioxide, and they pull carbon out of the ground too, right? Like minerals, pulling it out of stuff in the ground, limestone, and so they produce this energy-rich material that we eat, and then
when you burn a thing, you're mostly like you're putting oxygen back in, Like, you know how you can snuff a fire out? It goes out because it doesn't have
Runs out of
access to
material.
oxygen anymore. When you burn a thing, you're recombining the oxygen and the carbon and putting it back in the air mostly, instead of sometimes the dirt and the air, which is what plants will do. But there ends up being this problem on the other side, bluntly, simply boiled down to a carbon problem. There's too much carbon in the air right now for what we're seeing as the trends of what it's doing to the earth. But we need that carbon to produce the energy to keep life going. But there is a solution, which is solar. So never mind the solar piece, that's the efficiency piece, right? If we could stop bleeding energy out one side of this, there's an answer there. We're going to talk about that a lot in the next couple of
next
episodes.
dozen episodes.
The other side of this is if we can do what the plants can do and suck carbon out of the air and just put it in places where it fits in the cycle more efficiently and effectively, then we have, so this gets you to the technological solution that we're going to talk about with our guest, which is this idea of carbon capture as a thing that's possible. It's chemically possible for us to suck in a shitload of air through a vent and spit out bricks of carbon on the other side and oxygen. Nice, breathable, plant-like oxygen.
It happens all the time in nature, and this is where we've kind of reached the point in the conversation where it gets interesting as to what is happening right now, what's different about our world. When
we have to explore carbon capture options to solve this problem of this energy cycle, or
it seems like we need to explore that as a technology to meet the goals that we want to achieve here. But it's an interesting point in the conversation, because if you look at the world, pre-human, more specifically pre-human, like 150 years ago, the Industrial Revolution, we were in. It's hard to talk about this stuff without like hitting the cliches that like trigger me with green and environment and
right.
But
until we hit the Industrial Revolution comes into this, because until we hit that, the place where we slotted into this equation was basically still at the level of
we were in
animals.
balance.
We were farting, we were burning things, but there was enough plant matter to offset it and do the carbon capture.
Think of it this way:
us.
as a human, you can't produce carbon dioxide without eating a plant, and the plant can't exist without consuming carbon dioxide. And so I simplified the cycling there, but you're in balance on purpose because you can't not be, right? I can't exist if I wasn't eating plant matter, if I wasn't eating animals, and the animals can't exist without taking in carbon from the environment. And so before we invented all this fancy stuff, before we started driving cars around, we
to eat more plants faster than we ever have before.
Before that started happening, we couldn't get out of. It was hard for us to get out of sync, right? We could breed, right, which we've done a really good job of. There could be more of us, but even that, it was very, very hard for us to do anything that got us out of this balance in nature, right? And if you start to think about think about all the stuff humans have done. We built pyramids and we cut down all the trees in Europe to build boats and go to war. But you've got to recognize at that time, what you're still doing is cycling carbon that you didn't have the trees to cut down unless those trees consumed carbon from the atmosphere. So in a way, there was this balance.
And it takes trees a really long time to do that at a scale that satisfies our need for energy.
We just couldn't do harm the way we're doing harm now. We couldn't change the environment the way we're changing the environment now until we did something really, really crazy, and we discovered.
I think I just.
You hit the soundboard.
Sorry, take it back a few beats in your thought. Yeah, I accidentally hit the soundboard and put in a rim shot.
We couldn't change the balance of chemistry on the planet in an appreciable way as humans until about 150 years ago, when we discovered this crazy limitless source of energy. Seemingly limitless. We struck oil. We started using coal. We started using oil. We started using natural gas, and you can look at the time scales that we've actually been using these materials. And we were burning wood before that, which is kind of similar. But again, that's it's a surface. That tree had to grow kind of in your lifetime, or maybe the last couple lifetimes. So it's not like burning all of the trees that we burned in Europe through 2,000 years was just insignificant, because it was mostly in balance with the ecosystem. But all of a sudden, we discovered something underground, deep underground in the caves. There's like a deep, like Mordor component to this, right? And what it was, oil and coal, is literally millions and millions of years of these plants and little organisms that have died, and they fell to the bottom of the ocean, or they layered on and created soil. I mean, dig around in soil on Earth. Soil is not a natural thing on Earth. It comes from life. And so after millions and millions, and in some cases billions of years of this matter building up, it's all of the sunlight that those creatures captured over millions of years, compressed and pushed together and mixed and chemically reacted to create this extraordinarily energy-rich substance that we all of a sudden said, wow, we can pull this out of the planet and do something with it. What the hell do we do with this? And we started inventing machines. And then all of a sudden, instead of, this is where the transition starts to happen. Instead of having a farm full of people working and a whole bunch of animals that pull plows and do work on the farm, that was in sync, right? Those animals could only do work by eating plants, which consumed carbon, and then they exhale the carbon and it stays balanced. As soon as we pull oil out of the ground and start running tractors, we're not in sync anymore. It took millions of years for that oil to form, and now we're converting that back exactly like we did as people, right? We're kind of breathing it. The tractor is breathing out carbon dioxide just like we do, but it's breathing it out at unimaginably fast pace compared to what we used to be able to do. A tractor can just do more than an ox can, and it takes more energy for it to do it.
And it bleeds into the system. And if we don't have a way of pulling these things back into equilibrium, then the climate that we need to live in
changes.
Gets dicey.
It changes.
So the thing is, this kind of gets to that idea of tipping points, I think, which is a good way to start wrapping this up.
Wrapping it up.
But so we talk about the Industrial Revolution this episode. There'll be plenty more parts. We start talking about the Industrial Revolution. There's this tipping point where suddenly we're out of balance with the the flora and fauna of the system. It takes energy to make that energy. And we've been running this cycle that's kind of gotten us to this point. There's another tipping point coming where solar panels are almost more economically feasible to use to generate that energy. To create more solar panels, use them to get energy, is about to tip toward being just the best way to do it. So let's not chase the oil except for the things we really need it for, because we don't need it to burn anymore. And that relates to this carbon capture piece, which is what we're going to talk with our guest in the next part in climate change about, which is how to that space of what are companies up to in the space where we're about to hit this tipping point where it's going to get real profitable to use the sun to create energy to continue to drive these processes, which will inevitably get us to other problems. But I think what we've come down to is when you do the math, there's no way out of this that doesn't start from we need to develop technology, right? Reduce, reuse, recycle is an important part of it that everyone needs to learn, but that's not the answer because we're creating humans at too high a rate. We're creating animals that fart at too high a rate.
That
on our side of the system and the equilibrium.
Piece that doesn't get talked about as much because it kind of is counter to the argument of we need to stop burning fossil fuels is that we don't exactly need to stop burning fossil fuels. We can keep using oil. We can keep using coal. What we have to do is we have to stop putting carbon into the atmosphere at a rate at which we can't get it back out. If we could put big filters up in the sky like you have in your air conditioning unit to pull out carbon, then and they could capture carbon at any rate we want, we don't exactly have a problem anymore. There are other ancillary problems, like we'll run out of oil someday, we'll run out of coal someday, but the fossil fuel itself isn't the problem. There's just an imbalance of chemistry happening in our atmosphere. The cook in the kitchen of the planet had put too much spice in. They put too much salt in the food, and it tastes bad now, and we can't eat it, and we're going to die because we don't want to eat it. And so there's this interesting period now where we have to look at, well, where are we using fossil fuels, and what are they used for, and how do they get used, and are there alternative technologies that we can use to do those same things? How do we drive a car, right? 25 years ago, the only car was an internal combustion engine, and now everyone knows about electric vehicles.
And before that, the only car was a horse that ate some grass.
It was and it's important to recognize that the car and the horse are kind of the same thing. They're doing the same thing. They're using the same chemistry. They're using the same energy. It's embodied energy from the sun. We just have this weird, like, intermediate source of energy that is sort of the environment is not used to, and it's kind of unnatural in the sense of like how life exists on the surface of the planet right now. And so we'll get to all of these technologies and other conversations, because as you dig deeper into this, you realize how prolific fossil fuels are to modern society. They're used for absolutely everything.
On plastics,
and so you need to start to get this under control. You recognize, well, we need new technologies almost everywhere. Almost everything we do, everything we produce, everything that moves on the planet, including us, we need like different technologies
and new systems of incentivization, which is what the blockchain conversation is about. Look at it's about money systems.
Well, we've reached a point where we've maximized a lot of our efficiencies in markets because we've had this concept of, well, let the market do stuff. And now we're realizing, well, we're at a new meta level where we can gently start to manipulate, which is dangerous. It's a slippery slope, right? As soon as humans decide that they should start manipulating things. I mean, we manipulate markets already, but the interesting component here, and I think this leads really well into our next conversation, there's this huge opportunity to replace all of the infrastructure on Earth, basically. Literally everything, like concrete is an emitter of carbon dioxide because of the way we make it. We have to heat limestone to tremendous temperatures. How do we do that? We have to burn fossil fuels. We don't have another technology right now that's good at heating things up. So we burn stuff. And so concrete's all over the planet. Steel, same thing. You got to heat it up, drive your car, produce food, fertilize your field. So like everything runs on this right now. So if you look at it in the light of we have to do this, you can get into this like existential crisis of, oh no, the planet's collapsing. If you look at it all of a sudden from a business perspective, which is what we do in our next episode with our guest, is there's this incredible opportunity.
And is more or less what we do in our spin-off podcast, The Side Chain, if you want to check that out.
Good plug. Cryptos, right? And incentivization and change the manipulation of how people interact with stuff and how they make decisions and just how things operate. That's all this is changing the chemistry of how we do things.
Well, sir, that feels like a Zengineering AF place to jump out of here. Come back for the next part. Subscribe, like, and subscribe so you don't miss the next installment in the climate change series. We'll be talking to Gustav Alstromer. He's a partner at Y Combinator. So we get into a really cool conversation on all of that kind of stuff. I think we managed to stay out of the blockchain rabbit hole, but it was glaring at us the whole time. Thanks for hanging out for another episode. I already said like and subscribe.
Yeah, but you can't say it enough.
Special thanks.
Like and subscribe.
Oh no. And special thanks as always to our backers on Patreon. You know who you are. This stuff is it is very helpful. If you want to throw us $1 an episode to keep this stuff coming out, go to patreon.zengineeringpodcast.com. This is Zengineering.
Brian,
I'm Adam.
Take it easy, everybody.
Oh, farting animals.
There's a lot of burping going on too.